Good morning, everyone. Welcome to our session here. We're here to talk about how you can protect your data and secure your data for AI workloads in particular using tokenization. In the next 45 minutes or so, we're going to talk about one of the biggest friction points facing enterprises today, which is around how to secure your data and at the same time make it useful for your AI workloads and analytic workloads. We will also talk through how we navigated this journey at Capital One and share some of these learnings and talk through some of our key takeaways from those. By way of introduction here, so my name is Srikant Venkat. I'm part of the product team here at Capital One Software, and with me is my partner in crime, Vinayak. So we both will talk through different parts of this. I will cover some of the initial portion around motivation for this, as well as some of our key learnings, and then hand it off to Vinayak to wrap up the blueprints and other parts of the presentation. So here's the roadmap of our agenda. So we'll start with what we call the AI data dilemma. Essentially, we'll start by defining what the industry-wide challenge we face today around fueling AI with sensitive data without compromising the utility of the data and compromising the security of the data. In the second part, we'll cover what is tokenization, how that can help with maybe handling this dilemma and handling this sort of bottleneck that exists between the two. Specifically, we'll talk about the format-preserving nature of tokenization as one of the superior methods to encryption or masking or other techniques for data protection. We'll round this out with the Capital One case study, where we'll talk about, we'll sort of peel back the curtain on how Capital One went through this journey, how we built up our product stack, and how did we enforce this at scale that is demanded by our large footprint. At the end of this, we'll also share some learnings from this, some actionable patterns that you can take and use today for training LLMs or other models and building AI guardrails with this approach. So with that, let's kind of talk through what is this data dilemma or data bottleneck that we see today. Essentially, what this is the reality that a lot of us face today with enterprise data. AI is a top priority. Over 70% of enterprises today have projects that are centered around AI. Almost everyone here in the room has some AI project within your enterprise that you're probably looking to leverage data for. Businesses are aggressively pursuing this AI, with 70% of these organizations listing AI as one of the top 5 investments areas. For accelerating these coding tasks, for example, with your AI assistants or revolutionizing your customer experience, the potential for AI is huge. We understand that. But the value that you can get out of those AI investments depends on the value of the quality and quality of the data and completeness of the data that is used to train these models and is used at inference time. So as these AI models, we all know, is data, they are all data hungry. They need vast amounts of high-quality data and high-quality information to learn these patterns and make predictions. Significant portion of that includes sensitive data. So this could be your PII information, financial records, health data, and this creates a sort of a deadlock that we want to kind of explore. So you need this data to innovate, but using that data in the raw form creates massive risks, whether it's from a compliance or regulatory perspective. The most predictive data that you might have in your enterprise, these could be transactions, these could be health records, these could be personal identifiers, is also the most regulated and the most risky. So for businesses, this data is an asset and it represents the insight, but for the security teams, it poses a problem. How do we enable the secure usage of this data, especially for AI workloads? And you can see here some more statistics around the prevalence of privacy regulations that has kind of exploded over the past several years, and then the number of data breaches. So these are stats that I'm sure you've seen across the industry. The key part here is that this is also linked to almost the tripling of this data over the past several years. This is all net new data that's been generated, and how do we now use this all responsibly in our AI workloads for training and inferencing purposes? So that's what we'll talk about through the rest of this talk. So our approach centers around separating the this value from risk. So the idea here being that we break this deadlock by changing how we view the data. We need to separate the informational value of the data from the risk that it poses during use. We sort of have this framework called de-identify, analyze, and unlock that we found useful when we talk about this at Capital One. The first pillar of this is the de-identify part. So we replace the sensitive data with non-sensitive tokens, which ends up reducing the risk and sometimes even neutralizing this risk. So if the data gets compromised, the hacker steals the data, you still are protected because they've gained nothing of value. All of the data still is non-sensitive and can be safely used in these contexts. The second part of this, which is critical, is that it needs to enable your analytic use cases and your AI training and other AI-enabled workflows. For that, we need to preserve the format, we need to preserve the statistical properties and other desirable characteristics of the data and not lose them as you desensitize this data. And this allows all of these AI workloads and analytic engines to run with very minor modifications and not use that utility of the data that we had talked about. Through these techniques, if the risk is virtually eliminated, now you can open the floodgates. You can freely use this use this data through your AI data pipelines for model training, decision making, etc. So that's the approach that we are advocating for. And then we'll see how Capital One walked through this journey and talk through some of our learnings from there. So I want to kind of take a step back, and when we talk about protecting data, there is a spectrum or this landscape of data protection that you see out here. So on the left, you have methods like your deletion, masking, redaction. These are typically non-reversible. There are some cases where there's some reversible masking that has been attempted. And the key part here is that they are somewhat destructive to the utility of the data. So they're great for reducing the risk, but they also compromise the utility of your data. So as an example, you can't train your models, AI models, on deleted data. You can't train them on partially masked data, where only, let's say, part of your strings are available, part of your numbers are available in the form that is desensitized. So let's kind of look at this landscape through this lens. So say I mask a credit card number to reveal only the last 4 digits. I've secured the data, but at the same time, I've now compromised the utility of the data. So I can't train a fraud model where I only know the last 4 digits, and I can analyze those spending patterns. It's safe, but it's not useful. So how do we sort of overcome this is through the other 2 methods that you see on the right here. So on the right, we have those reversible methods where with encryption or tokenization, we can reverse the process and at the same time be able to preserve all of that analytic value is not lost in the transformation. Both allow you to get the original data back if the user and in the context in which they're using it, it's authorized. And you also have access to other key material and other things that you need to reverse that transformation. But there are critical differences between the two. So we want to touch upon a couple of those and then talk about why we went down the tokenization path and how we sort of affected that at Capital One. So if you look at the key differences here, traditional encryption deals with data at rest. So it takes let's say your 9-digit social number, turns it into a string of alphanumeric or numeric characters. The problem is that unless you're using a format-preserving encryption, it breaks your database schemas, it breaks any validation logic, and most importantly, your AI models tend to be confused because they can no longer see the shape and the characteristics of the data. Tokenization is slightly different from this approach. So what we do there is we replace this with another similar formatted string, and it looks like a credit card number. It passes the validation checks, etc. It fits in, with whatever the referential integrity constraints you might have on your database columns. So to your applications, whether the analytic applications or AI models or pipelines, the data looks real. But to a bad actor, it's meaningless. So even if it's compromised, it is just a bunch of tokens that don't have any value or correlation to the sensitive information. So this format preservation, length preservation, all of these characteristics allows us to secure the data in use, not just at rest. So you can now do joins across columns, and the magic key here for AI is that all of these downstream applications can now literally consume this data and be able to provide the same level of accuracy and fidelities. And we'll share some results around this as we talk through this process. So the concept is summarized in the graphic below. So you see the original social security number is put through a tokenization engine, through APIs, et cetera, and then out comes this string that is formatted exactly like the original social security number with the 3, 2, 4 with dashes in between them. And then that is how it's stored. So it's stored as modified, and that makes it easier for these business tools and others that are using this to be able to utilize that in the same fashion as they were with the original data. And then you can now safely do your joins and preserve the analytic values because there is consistency in terms of that operation. So if A goes to B somewhere, then A goes to B everywhere that you see A in your data. So that's the value that you see here, and that's one of the reasons why we went with the tokenization approach, which we found is far superior to any other data protection techniques that we talked about. So in particular, what are the key benefits that we get with protecting your sensitive data using tokenization? Beyond just the format preservation, modern tokenization systems offer sort of the security hygiene for the cloud. So what we mean by that is we have simplified key management. So we are managing a key for every single read operation like you would have to do with encryption. And this becomes a huge bottleneck in the performance and brings up latency and other issues that you'll encounter with the whole encryption space. The second piece is around the referential integrity. So the same input always creates the same token. This means you can perform your joins safely across different databases using the tokens without ever reversing that tokenization process. The third piece that is also critical here is that we embed metadata such as versioning and other logic inside of the token itself. So this allows us to do key rotations, for example, and then the system knows a priori how to detokenize this based on the token itself, which allows us to do this key rotation as well as access any sort of bad or compromised data when that happens. And then we can now safely rotate this without touching the raw data. So this gives us a huge benefit in terms of management of this over time as changes happen. The other two key pieces mentioned at the bottom here are the preservation of the analytic value, which we already touched upon. And because of this, the architecture of this tokenization solution that we'll talk about, the brute force key compromises become virtually infeasible. So we'll see how that is possible with in the next few slides. Okay, the other key question that you might be wondering here is, does the tokenization actually hurt my model's performance? We did a study, and we'll be releasing the results of this in the next couple of weeks, where we did a study comparing three data sets. So the original raw clear text data, mass data, and tokenized data. And we used those to train models. And then we saw a dramatic improvement in performance with the tokenized data. So you see the red box there represents the accuracy of the masked, the data using the models using the masked data that drops it from the clear text baseline of 100% to 50%. In the world of prediction, 50% is obviously not the greatest, just the same as a coin toss and practically worthless. On the other side, when we use tokenized data, we were able to preserve that accuracy. So 99% of plus percent of the predictive accuracy was retained with the clear text baseline data. So what this means is that you can now train your models on safe, compliant data and still get the same results that you would that are virtually identical to training that on the raw sensitive data. So you get nearly identical model performance with virtually zero risk with this. So that's why we went down this path of doing all of our data protection anchoring on tokenization. So shifting gears a little bit, let's maybe look at the concepts here. So we looked at what tokenization offers us. Let's see how that is actually done in practice. So here's a little cartoon that explains this. So you'll see on the top here, so the sensitive data, this could be a social security number that is being fed into your applications. The tokenization engine, API, whatever you're using, will request token, so all of the crypto material and all the magic with all the algorithms behind the scenes will convert that raw sensitive data into a token that preserves the format and length, etc., and then it returns that token that you see there starting with the 5C7. And that data is now stored in wherever your wherever the original data source is. And then the applications can now safely use that proxy or the surrogate token wherever the original data was needed. And because of its format preserving, length preserving, all of these other characteristics, we can now use this consistently across your entire landscape, and you won't lose any referential integrity issues. You won't run into this. But how do you actually implement this in a modern cloud-native sort of environment and without bringing your operations to a grinding halt? So that's how we want to talk about next in our case study with Capital One. So our journey with tokenization began around 2016. We were a traditional bank. We had a lot of on-premise data centers and lots of data over there, but we made this very bold decision in 2016 to go all in on the cloud, on the public cloud in particular. By 2020, we had completed this transformation, exited our data centers entirely, and we were the first major bank to do so. But that migration came with a sort of a little twist here. So we had to move these petabytes of data in highly sensitive financial data into the cloud, and our old data security approaches couldn't keep up. So they became bottlenecks for us. So how do we kind of get over this bottleneck? We looked at a lot of technologies out there, did a lot of evaluations of these, and we found out that there's nothing that could offer the performance and scale that we needed for our data. So we ended up building our own engine. So we built our own tokenization engine from the ground up, and designed it specifically for the elasticity and other characteristics that we needed in the cloud. So that engine has become like the de facto standard and core pillar of our data security across Capital One today. And it kind of underpins our entire data security strategy at Capital One. So we took these learnings, and then we realized that, hey, there is a huge amount of value here that we can give to other enterprises outside if we share this technology. So we decided to productize this through the Capital One software entity that we formed in 2022. And then we launched this product as what we call as Databolt in April 2025 at the RSA conference earlier this year. And this is what we will talk about in the rest of this presentation of what the benefits are and how we, what that has netted us, and some patterns that we've learned in the usage of these kinds of technologies in terms of securing data at scale with cloud-native environments. So just to kind of give you a bit of context around this, the scale of this whole tokenization engine and how it's used at Capital One, we protect over 29 different types of sensitive elements, everything from your social security numbers to dates of birth or customer account IDs, etc. Over 900 applications, all hitting this massive tokenization infrastructure internally, and then billions of records where across our enterprise that are used. And then all of this is AWS native. So when you operate at this scale, latency is it's not just an annoyance, it becomes a failure of the design. So we've very carefully architected this tokenization engine to really be very highly performant and have very low latency. So what this means is that as a digital bank, we really need to have a real-time, highly available, fault-tolerant service that we can rely upon to be able to do this. So that's what we've built, and we'll talk through some of the characteristics of this, and Vinayak will do a deep dive into some of our learnings from there and how we can kind of expand the footprint of these use cases that we can address, especially from an AI perspective with this solution. Okay, so one of the key underpinnings of our tokenization solution is the concept of a vaultless tokenization. Traditional tokenization approach, you have relied on a vault, which is a massive central database, which maps your sensitive data to the tokens or the proxies or surrogate values. The problem with this is that because it's a database, it quickly becomes a bottleneck. Every time you need a token, you have to do a database lookup. And because of that, it adds latency and creates a single point of failure. And it also becomes a massive attack vector for your hackers. In effect, your vault becomes a honeypot. So if a hacker breaches this database, they have keys to the entire kingdom, so mapping every piece of sensitive information that you have. So we thought long and hard and came up with a solution for this, which is what we call the vaultless architecture. So we use a deterministic algorithmic approach. We generate these tokens with crypto algorithms that are now even quantum safe, rather than database lookups. This offers infinite scale for us because we aren't limited by the database I/O in this case, and it gives us the nice characteristics of highly performant and the tokenization operation itself having very, very low latency and overhead, so it happens in microseconds. So this enables real-time use cases such as fraud detection that were previously very difficult to achieve with a vaulted approach. So we kind of anchored our tokenization engine on this key sort of scaling and artifact. So as we built and matured this tokenization engine within Capital One, we saw the opportunity that, hey, this is a universal problem. So how about we think about helping other enterprises by commercializing this technology outside of Capital One? So as part of Capital One software, we launched this product called DataBolt back in April, as I mentioned before. And this is designed with all of these elements that you see here. So it provides you the same advanced security models. It gives you the cloud-native architecture, and it gives you lightning fast performance, and it represents an evolution. So we did added a few bells and whistles on top of our tokenization engine for this to be consumable outside of Capital One as an enterprise. So in particular, there were some architectural elements that enabled us to do this. This is where we have a separation of duties. So we have a control plane where you manage all of the metadata, the policies and keys, et cetera, and these sit securely in Capital One's cloud. Then there's components that you drop into the customer environments where the tokenization happens actually. So what this means is that it happens within your network. Your data never leaves that environment and comes into the Capital One plane. Only the metadata is provided there. And then you keep custody of your data. We never see your sensitive information. So we built with all of these architectural and other constraints in mind. And then Vinayak will walk you through the product and the capabilities there, and also some of our learnings as we build this and scale this. Over to you.
Thanks, Shrikant. Hi, everybody. My name is Vinayak Lavle. I'm the Senior Distribution Engineer at Capital One. I would like to take next few minutes to peel back the layer of this architecture at very high level. As you can see, DataBolt operates on a hybrid deployment model, which is designed specifically for the security and resiliency. On the left side of your screen, you see a control plane. That control plane is deployed within Capital One Software's cloud environment. It handles the management traffic. By management traffic, I mean the configuration, the access policies, and it also serves artifacts like SDKs, UI documentations as well. This is the place where you go and configure your SSO. This is the place where you go and see your audit, analytics dashboards as well. On the right, you see a data plane. This is our core engine. This entirely runs within your ecosystem, as Shrikant mentioned. So every operation is within its own memory. That means this sensitive data is not going outside of that process and your network boundary as well. This data never reaches our control plane. So you can be very sure that Capital One does not have access to your data. And this data plane can run in your AWS VPC, on other cloud, or even on on-prem data center as well. The critical part that I talked about is all these tokenization operations are happening within the memory. That means we can do these operations very fast. You don't have to basically do a database lookup, as Shrikant mentioned earlier. The other thing that I would like to talk about is I get asked a lot, what happens if control plane goes down? don't worry, we built this for resiliency. When the data plane boots up, it basically establishes a secure channel with the control plane to fetch its configuration and the cryptographic material. And we take this communication path very seriously. We don't want anybody to save this traffic and decrypt later. So we use a NIST-approved post-quantum safe algorithm on top of regular TLS to secure this traffic. Once initialized, this data plane caches this information in memory and continues its operation. So in the event the control plane is unreachable, the data plane can continue its operations autonomously. Your workload will continue running without a hiccup even if control plane is not available. This share nothing runtime approach ensures that our availability issues will never become your availability issues. Let's go a little deeper on the benefits and the characteristics of a data vault. Shrikant already alluded to the fact that we use a vaultless architecture. In a traditional vaulted architecture, you have a massive central vault. And you store mapping between your sensitive data and the token in that vault. It works for the small data sets. But when you scale it to the enterprise like bank, it quickly becomes a bottleneck and a massive cost center as well. And Shrikant already mentioned about the security issues that it brings. That's why we chose vaultless architecture for Data Vault. Data Vault uses deterministic and format preserving algorithms. We don't store the mapping, we compute that mathematically. And since there is no database lookup, I've repeated this many times, we can offer a single low digit millisecond latency for this operation. So you can scale infinitely. You don't, if you need a high throughput, you just need to spin up more data plane pods, and you get that for free. Now regarding security, being from Capital One, we are very paranoid about the security. In our internal implementation, we assume that the host is compromised. That's the reason we have employed advanced memory techniques to safeguard this cryptographic material in memory as well. These keys which are in memory are scrambled in such a way that if the bad actor gets access to the host and it dumps the memory, they will not be able to extract the keys from that dump as well. It will be practically infeasible. And we carried these security measures to Data Vault as well. We also support tokenization on write via our SDKs, which can seamlessly integrate with your code in the platform like Snowflake, Databricks. And for monitoring, we use OTel. That means our customers don't have to use, they can use their existing monitoring tools to monitor Data Vault. Moving on. In our experience, for most enterprise organizations, analytics is the first use case for tokenization. The data dilemma that Shrikant talked about is the most acute here. You have data scientists, analysts that want they want access to high fidelity production data to build models, to run reports. But you cannot give them access to raw PII data. Historically, organizations have used masking, but masking is just, they just replace the data with asterisks. That destroys the data utility. You can't join table on a masked column. Our blueprint is very simple. Land your data tokenized. Whether it is S3, Redshift, Data Vault, or Snowflake, use the Data Vault SDKs in your ETL pipeline to tokenize the data the moment it enters your analytic environment. This gives you two things. First, security at rest. So let's say if someone incorrectly configures your S3 bucket, that results in a data breach leaking your data. They get just the access to the tokens, not the actual data. And in fact, for our internal implementation, we had this issue, and our internal tokenization saved our face because we had the data tokenized in that S3 bucket. The second is the granular access. With data at rest being tokenized, you can implement on the fly de-tokenization for reads for the authorized users, so that only authorized users can get access to your raw plain data, and your data is secure. So let's look at the concrete implementation of this pattern using Amazon Redshift. This is from one of our early customers. They needed to expand access to their data warehouses to all analysts, but they wanted to make sure that the raw PII is accessed by a select few analysts. So here is how they set it up. They deployed the Datable data plane in private subnet of their AWS account in the existing EKS cluster. For the execution flow, they used Redshift's masking policies and UDF features. When an analyst tries to run a query like select star from customer, the Redshift invokes this UDF for the sensitive columns. And this UDF triggers a Datable to connect a Lambda. This Lambda acts as a bridge to the Datable data plane. This Lambda authenticates the call using IAM policies and then passes the call to the data plane to get the actual value for the token. Data plane consults its predefined access policies, and if the authorization is correct, it will return the actual value, otherwise it will return the same token back. The result, the analyst continue using their standard SQL. They don't have to worry about the heavy security lifting that goes in the background. One thing I would like to also note here that we are also working on a Lambda native data plane that will remove the need to run the Kubernetes cluster in the AWS environment for the use cases like this. Okay, so now analytics is the immediate need, but the new frontier is obviously the AI workloads. Interestingly, the architecture I just described applies almost identically to AI workloads as well, just that the value proposition shifts slightly. In analytics, you may need to see the real data again, but for the AI workload, you almost never do. If you train a model on masked data, I think Shrikant went over this, the model learns nothing because it's just a string of asterisks. But with tokenization, the feature set is preserved. Like Datable preserves length and format. So your SSN is nine characters long. Your tokenized email has that @ symbol and domain in the token as well. This means you can train your small language model or fine-tune your large language model on fully tokenized data set. The model can learn the patterns like people with X zip code tend to buy product Y, like these use cases, without ever absorbing the actual PII into its model weights. This also effectively eliminates the model inversion attacks. These attacks are basically trying to extract the original data from the model. This is what the pipelines look like in AWS. It's very straightforward. You have your raw data in S3. You can use glue data catalog to tag sensitive columns. Then Datable can ingest this metadata, and it can create a tokenized replica of this data set. Then you can point your SageMaker training pipeline to this tokenized replica. The result that you get is the high-quality model that is already compliant because it never saw the sensitive data. Okay. Finally, let's talk about the in-demand use case, that is GenAI applications. GenAI applications requires proactive as well as reactive controls. When you deploy chatbot or chatbot-like application, you are opening up a new interface to your data. And users are unpredictable. They can always enter sensitive information in their prompt. You cannot rely only on the safety training of the model for that. If you rely on that, that means you are taking a risk. Also, there are sometimes legitimate need for the downstream application to reference what user has in their original prompt. So you might need access to what user have entered. So for use cases like this, we recommend sandwich approach. First, pre-processing. You tokenize your sensitive data before it leaves your environment. Then post-processing, when you get the response back from the model, de-tokenize and return it to the downstream applications. This slides illustrate that flow. If you see in the middle, there is an orchestration service. It acts like a traffic cop. It receives the user input. It calls scanner to detect to see if there are any sensitive elements in that input. If it found, it will call Datable to tokenize that information, and then it will replace the sensitive information with tokens and then construct the prompt again, and then that prompt gets sent to like Bedrock, any LLM hosted in the Bedrock. And after receiving the response from the LLM, if it has sensitive elements, it will again de-tokenize and then send back the clear answer to the application or user. This keeps PII completely invisible to the model provider. This also solves your data residency and privacy concerns with public LLMs. Okay, to wrap up, whether it's for like traditional analytics or the emerging AI workloads, vaultless tokenization ensures you stay compliant without slowing down your innovation velocity, and Datable can help you in that space. Thank you for your time. I will hand it back to Srikanth to cover the key takeaways.
Right. Thanks, Vinayak. All right, so we have 3 key takeaways here that we talked about. The first part is how do you unlock your data? So addressing this whole issue with this data dilemma that we saw before, where you're balancing the utility value of that or informational value of the data along with the security risk that it poses. So how do we do that? And then we identified and showed how tokenization can help you as one of the strategies to help you prepare for that. Then the second piece that we talked about is around the architectures, the cloud-native architectures designed for the scale, performance, latency needs of a large enterprise with petabytes of data that we have in the cloud. So some of the characteristics that we saw that helped us around implementing these as a vaultless federated architecture, and then also providing, using the native services on AWS to enhance some of these for the scalability side. The third key takeaway here is that we always want to build this as defense in depth sort of layers. So tokenization can be used as one of those layers, as Vinayak mentioned, as a data-centric guardrail, for example, that gives you these proactive and reactive controls, and then gives you the ability to use your data responsibly and safely without worrying about the risk that it poses. So you can go from blocking your AI use cases due to the risk to enabling those with confidence with the data protection built in through these layers. So these are the key sort of learnings that we wanted to share with you, and also kind of talk you through this journey so that you can use these in your day-to-day challenges that you see with your enterprise data. So we'll stop here for the presentation side of the house. We have a couple of call to action here, so please do visit our booth. And then you will see on the chairs the AirTag holders, so you can go and collect the AirTags from our booth. So we welcome you to come and see us there. Then we'll show you a demo of Datable in action. We also have an upcoming webinar where we talk about the study that we alluded to here, where we looked at training the models on mass data, the clear data, as well as tokenized data, and we'll share some of the results that's upcoming with PwC on the 12th. Essentially, these are key next steps in terms of how we want to proceed with this, and we'd love to kind of get your feedback and questions. We have a few minutes left here, so we'll pause here and take questions. Thank you.